Okay, physics time. Today is the day that we have all been waiting for when we get to the truth of physics, which is called physics. The true and more or less veiled nature of physics is relativity. And I hope I remember to readdress the fact that I said that before the end of the video. Something I'm actually kind of bad at. I'm oftentimes, as I review my videos, I'm oftentimes saying things like, oh, we'll talk about that later, and then later comes and we haven't talked about it. The end of the video comes and that's never been brought up again. But you'll see, I hope, why I mean the truth of physics has been veiled this whole time by the end of it, even if I forget to re-mention it. Your book starts out by saying this: everyone, every single human being who has ever and will ever live, it says, knows that we move in time at a rate of 24 hours per day. Everyone, it goes on to say, knows that we can move through space at rates ranging from a snail's pace to those of supersonic aircraft and space shuttles. But, it says, and I love this, but it says, relatively few people know that motion through space is related to motion in time. And the fact that I think that's funny is because it says relatively few people. Relatively few people understand. What do relatively few people understand? Your book claims relatively few people understand relativity, basically. That space and time are, what's the next word I'm going to say? No, related. And now we're going to do something I think is really cute up here, which is this. Relativity and related. Those are all these words are, even these words themselves are related in what way? No, what is the word? What I'm getting at, and this is where we usually start videos like this, is what does relative mean? Yeah, they're maybe similar. We're kind of getting some synonyms because this is a really tough word to define, actually, because it's a hard word to define because it's such an inextricable part of our process of definition that we as human beings, even without knowing the word relatively or related or relativity, we relate things together. If I want to talk to you, if you've never, like in Plato's cave, you've never seen an actual tree before, and I want to describe a tree to you, I might say, it's like this shadow of a tree. And in saying like, I am relating it. If you've never seen a fish, and I want to say to you, a fish is like a cat, but it swims all the time and it doesn't have any fur. The word like there, I am relating that. That's what relating means. In fact, even my telling you about relativity is relating to you what I hold to be the truths of the ideas of relativity. So all these words are related. They are all similar. They're all, we could say they are in conjunction with each other, in conjunction with each other. But effectively, when we say that things are related, we're saying that there is some relationship. They're in some way, as you said, Tatum, they're in some way like each other. Or in some way compared to each other. Or in some way how the other one is. I'm relying kind of on my very faint knowledge of Romance languages here, French and Spanish, because in those languages, like and compared to and how they are is all the same word. Como in Espanol and como en français is all of this. That one word encapsulates all of these things that relate to each other. We've talked about relativity before in class. We've talked about relative motion. Let me underline that in green too. Relative motion is like when your aunt or your cousin is coming down the stairs and you push them off the staircase. That's a relative in motion. Relative motion is like when your grandma is using a wheelchair ramp and you just send her down it. That's a relative in motion. Relative is like when your baby cousin comes to visit and you throw him up in the air, and then whether you catch him or not is not really for me to decide. But no, I'm joking. But even though this is a joke, is this word, the way we use relative like a family reunion, does that have to do with these? Yeah, your relatives are in a way like you. They're in a way in conjunction with you. They're in a way similar to you. They're in a way compared to you. They are more closely related, there's that word again, than random people. to some extent. In 8th grade science and earth science and physical science, we talk about, I'm going to make this as a little side note, relative age dating. And I make the joke in those classes about relative age dating is not when you're at the family reunion and you're trying to decide who to date based on how old they are. Although that is, I think that's a funny joke. That's on the edge of inappropriacy. I don't recommend that. But relative, again, means like or compared to. So in all these ways, we're discussing the way things are as compared to other things. Relative motion, we said at the beginning of the year. You can go back and watch our video about this. But relative motion is motion as it's compared to something else. Without ever saying specifically what we're relating it to, what do we relate motion to on planet Earth? Almost always. If I say Justice's mom is driving their Jeep, Cherokee, Grand Cherokee, down the highway at 65 miles an hour, I need to relate that to something. What am I inadvertently or without saying so, unvocally saying I'm relating that motion to?
Someone who's not driving or moving.
Okay, somewhat more broadly though, something or someone that is not driving or moving compared to what? Because all of this is moving compared to the sun. Right? Usually we just compare it to Earth's surface. So the motion that we talk about kind of in a lackadaisical daily way is compared to the motion of the Earth's surface, which to us we think of as none. But all motion is relative. And space and time, back to our main point, space and time are related. The more, let's write this down, the more an object moves through space, the less it moves through time. We saw this in our Vsauce video. I don't think Vsauce is copyrighted, but if it is, don't come at me, Vsauce copywriters. The more an object moves through space, the less it moves through time. We saw this in the Vsauce video where it said that basically compared to what we might call a stationary observer, an observer whose reference frame isn't changing, an object that is moving experiences time more slowly. And since motion is relative, they perceive you as moving, and they perceive your time as moving more slowly. And so it seems to us that those things can't mesh, but we'll talk about how they do. Basically, space and time are one thing. Space-time. The idea of the Newtonian idea of space as kind of a vacuum where things happen, and the Newtonian or sub-Newtonian idea of time as the rate at which things happen are both flawed. Neither of those is wholly correct. We now understand that they are one thing which we call space-time. And as we move through space, we're also moving through time. And as we move through time, we're also moving through space. All of us, everything. Your motion. Let's say, okay, so let's think of two examples here. Here's you walking. These little feet represent that you're walking. That's you. And this is your ponytail, obviously. This is you in 31 minutes walking to lunch. That's you. You're walking. You're moving at some rate. And now compare that with, let's say, the Starship Enterprise. Other brands are available. Please do not come at me, Viacom. There's the Starship Enterprise, and it's moving at almost light speed. We'll say 0.9 c. Space-time is 1. Both of these are moving through space-time. You moving at basically 0.00000000000000000000002 c, right? Some quadrillionths of the speed of light. I don't know. I'm not counting those numbers. This is for effect, not for actual mathematical accuracy. You're moving at a rate very, very much less than c. BT dub, what's c?
Speed of light.
Speed of light, which you need to know, which you do know, and it's also mathematically, Tim, as you said, 3 times 10 to the 8th meters per second. If you don't have that, you need to write that down. If you don't have it in your memory, you need to memorize it. Anyway, in this example of you here in half an hour moving to lunch, you're moving mostly through what?
Time. Space.
Time. You're barely moving through space at all. right? Your motion through space is small.
And you're saying space like outer space?
No, I'm saying space like, in general, three-dimensional space that we normally talk about. So you're barely moving through space at all compared to what? Compared to the Earth. You're mostly moving through time. So you're moving through time at a rate of about very, 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 very slightly less than, compared to Earth's surface, very slightly less than 1 second per second. Because time is slightly, we say, dilated, slightly slowed for you because of your motion, but you're mostly moving through time. The Enterprise, on the other hand, is moving very quickly through space, and so it very, very only barely moves through time. So we, as outside observers, see the Enterprise's time as going slower. Time will seem to go slower from us observing them. Now, this is a very important part of relativity, is that to an outside observer, now I don't mean outside the universe, I mean someone who's not, someone to whom the motion is relative. To an outside observer, objects moving more through space move less through time. So what does it seem like? If they're moving less through time, basically it seems like their time is slower. It seems to an outside observer. Now let me make it very clear that if you are Captain Picard and you're on the Enterprise, this is how Captain Picard rides the Enterprise, surfs on top of the saucer section like that. If you are Captain Picard, to you the time does not seem any slower. Does you or you? To you, this other guy, this guy just walking, his time seems slower. So what gives? How can those things both be true? How can we see this time as slower and this guy seems this time as slower? Well, because it's all relative. It's all relative. Your book goes on, and I would like you to read this, but your book talks quite a lot about, it goes on, I think, let me tell you the page number. The twin trip is section 15.7 on page 222, and it talks about how there's a pair of twins. One of them goes in a rocket at a certain percentage, a fairly large percentage of the speed of light, and they're gone for X amount of time, and when they come back, the twin who had stayed is older. Time passed more slowly, effectively, for the one that was out. And the reason it isn't the other way around, the reason, even though this seems slower to this, and this seems slower to this, is because the initial twin was originally in the same reference frame as the first twin. If they both lived their whole lives in the way that one was moving slower and one was moving faster, to us, they wouldn't notice a difference at all. It's because the one started out at rest and then moved that it seems like he didn't age as fast. Because it's all, what word? It's all relative. The nature of the universe is relative. The nature of the whole universe is relative. One thing, how it relates to each other. It's all, another way we can say this, is connected. It's all connected. You can't tell the motion of Mariah Nelson driving her car over to Westco without saying compared to or connected to something else. If the whole universe was just Mariah Nelson's car as a single object, there would be no speed. That doesn't even mean anything because there was nothing for it to connect to. This is why sometimes students have such a hard time learning in general, because they have very little to connect it to. The nature of the universe is connection. The nature of the universe is interconnectedness. What links these two things? In addition to the fundamental nature of the universe being relation, connectedness, the fundamental nature of space-time is this. This, even though what I just said is true, time seems to move slower for this compared to this, and time seems to move slower for this compared to this, both of these people observe c, the speed of light, to be the same. It is constant. That's why we abbreviate it for c. The speed of light is the same in any frame of reference. That's called the second postulate of relativity. The second postulate of relativity. Let me spell relativity correctly. All observers agree on the speed of light. Always. And I'm tempted here to write the speed of light in a vacuum, but as you saw in Vsauce, the speed of light is actually true all the time. We know physically, in classical physics, that light will, in quotes, slow down as it moves from air to glass to air to water and back out again. We call that refraction. But in reality, the light doesn't actually slow down. It just interacts with particles along the way, and so it takes a longer path, and therefore appears to us to slow down. It basically has farther to travel between these particles. The particles, in a sense, block its path. And so the light doesn't actually slow down when it's refracting. It takes a slightly longer path, a slightly more labyrinthine path. And so in reality, the speed of light is always 3 times 10 to the 8th meters per second. The second postulate of relativity says all observers agree on the speed of light. Now, how can that be? Since this one's moving almost the speed of light, won't it see light as being slower? In the same way that, like, when you're on the highway, you think that the 18 wheeler coming up to pass you is only moving about 2 miles an hour relative to you, right? You're both moving quite quickly compared to the ground. So wouldn't it be the same to light? Wouldn't the Enterprise see light as only moving a tenth its speed? No. They must agree to this because this is a fundamental truth of the universe. This, agreeing on the speed of light, is truer than this. These two things, which we normally think of as completely immutable, we think of time as unchangeable, and we think of space as more or less unchangeable. But these two things change themselves. They give way to the speed of light. Basically, even though it seems like the Enterprise should see light is going slower, both the distance that the light must cover, space, and the time that it takes to do that, time, conspire. They work together to make this true for our universe all the time. That's the second postulate of special relativity. The first postulate of special relativity, which maybe, you could argue I should have said it first. The first postulate of relativity, which I've spelled wrong again, I don't even care. I'm just going to cross it out. The first postulate of relativity is that observers in a frame of reference agree upon the laws of physics. What do I mean by the laws of physics? Yeah, stuff like Newton's law, stuff like universal gravitation, stuff like speed and distance and time. So within a certain frame of reference, on the Enterprise, when Captain Picard is walking to go talk to his friend Will Riker, who's taller than him, on top of the Enterprise, even though they, to us, are moving at 9/10 the speed of light, to each other, all the laws of physics are the same in their local environment. That's the first postulate of relativity. Space and time will both dilate. What's the word dilate mean? Yeah, get larger. Fluctuate is maybe a better word, but they will both dilate to accommodate both space and time. Or space-time, yeah. Both space and time as we think about them classically, two separate things, but also in a realer sense, space-time, the fabric of the universe, will dilate to accommodate the speed of light. So the changes that space and time both undergo, as seen by outside observers, conspire to make C true. That process is called dilation. A neat effect of this is that the Enterprise here, moving at 9/10 the speed of light, we'll get into the math in a second, but the Enterprise moving at 9/10 the speed of light, to us, if I say that a star is 2 light years away, you with me so far? A star is 2 light years away. How long will it take for light to reach that star? 2 years. That's the definition of a light year. A light year is how long it takes, or sorry, how far light will travel in 1 year. So to us, that takes 2 years. But to the Enterprise, if it's moving at 9/10 the speed of light, time dilates, and so it can get 2 light years away in what to it seems like maybe, we can do the calculation itself, but I'm going to say maybe a month. I don't know. Because the time itself has changed. The speed of the Enterprise both makes it, the distance seem shorter and the time seems shorter to the Enterprise. And so a neat effect of that is that when we start talking about interstellar colonization or something, which we're not really at that point technologically as a society or as a species, but when we get to that point, it's actually a little bit, relativity actually makes it a little bit easier, because if we're moving at what we call relativistic speeds, speeds in which we have to account for relativity, both distance and time shorten our trip there. So even though it seems to us like light would take 2 years to get there, or the Enterprise would take whatever 2 divided by 1.9 is. No, 2 divided by 1.9, which would be what? That's not right. What's 2 divided by 1.9? Sorry, 2 divided by 0.9. I was saying it wrong as part of the problem. 2 divided by 0.9 is the same as 2.222 repeating, yeah. So even though to us it would seem like the Enterprise was taking 2.22222 years to make that 2 light year trip, to the Enterprise it would seem like much less time than that, because space and time dilate as it moves. Do you have questions about the concepts of relativity? Why we use the word relativity, how space-time is one, and how everyone agrees on the speed of light. Do you have questions about this so far? We're not done yet, so don't put that away. In fact, keep that out, and you should probably get yours out too, Tatum.
So when you say dilate to
accommodate the speed of light. It dilates to accommodate the speed of light. It dilates to make it so this is always true. Space and time change. The very fabric of the universe, space-time, changes so that c is always true. C is always the speed of light. A couple things we're going to talk about now mathematically. One is called the Lorentz transformations. Did I erase this too soon? Is that why you made that noise? Okay. One is called the Lorentz transformations. Named after an Italian physicist, Lorentz. And this is how objects change as they approach relativistic speeds. How objects, I'm going to put appear, Lorentz transformation. How objects appear to outside observers, again there's that phrase, to change as they approach relativistic speeds. One is that to an outside observer, length seems to contract. Your book wants me to remind you that a rule of relativity is that changes due to alterations of space-time. Remember, why would space-time alter? What do we call the alterations of space-time? First of all, what's the verb? Alterations of space-time are called dilation. Good. Why do those happen? To accommodate the speed of light, to make it so the speed of light is always agreed upon by all observers. But it says a rule of relativity is that changes due to alterations of space-time are always seen in the frame of reference of the other guy. So even if you're the one who you know conceptually you're moving, relative to Earth, say, you're going to see these changes occur to the other stuff, to the outside stuff.
What is the last thing?
Approach relativistic speeds. The first Lorentz transformation is this. L equals, you ready? L sub naught times the square root of 1 minus the quantity v squared over c squared. L is the perceived or the apparent length. What do you think I mean by a perceived or apparent length? As perceived or appears to whom? Mm-hmm. L is the perceived or apparent length as seen by an outside observer. L sub naught is, well, what do we use sub naught for in physics usually? This little 0 down here usually means, it usually means, no, not final, initial. It usually means the initial. So this is what the, we could say the rest length. If it's not moving compared to an outside observer, the rest length. 1, you know what 1 is. V, guess what V is? Velocity. Again, I should probably qualify that by saying perceived or apparent velocity compared to what? Yeah, well, usually to Earth's surface, to an outside observer, it would say. And then C, of course, is the speed of light, which is not only do we know what it stands for, but we also know what it equals. 3 times 10 to the 8th meters per second. So basically, the faster this thing is going, the greater the what? V, right? You with me so far? Faster it goes, the greater the V, the more this approaches what? Well, let's think about what would happen if the velocity here were 0? What if we were all resting? Let's actually take a very practical example here of this meter stick. What do we agree the rest length of this is? 1 meter. 1 meter, right? If V is 0, check out what happens. What's 0 divided by the speed of light squared? 0. What's 1 minus 0? No, what's 1 minus 0? 1. Boy, that was a hard question for you juniors in high school. 1 minus 0, in fact, is 1. What's the square root of 1? 1. So this whole thing, if V is 0, this whole thing becomes 1. Okay? So the apparent length, or sorry, the initial length, the rest length is 1 meter times this whole thing is 1. What do we see as the perceived length if it's not moving? 1. So if we have, let's just do this whole thing. 1 times the square root of 1 minus 0 over c squared. That whole thing is 0. 1 squared, or sorry, the square root of 1 is 1. 1 times 1 is 1. In this case, 1 meter equals 1 meter. So at non-relativistic speeds, 1 meter is 1 meter. When this is still, 1 meter is 1 meter. Yeah? What if this is moving at the super high rate of 30 meters per second, which is about 60 miles an hour on the highway? Well, let's do that one together. So we have L, we're going to try to find the perceived length, equals 1 meter, right? That's what we agree the rest velocity is, times the square root of 1 minus 30 meters per second squared. Sorry, let me make that a little bit clearer. 30 meters, the quantity 30 meters per second, that squared, over 3.0 times 10 to the 8th meters per second, that quantity squared. So in our calculators, we type it. 30 squared.
1.
No, just you do it. I tell you. Oh, you already got it?
Yeah.
What?
1 times 10 to the negative 14.
Yeah, it's just, what? No, it isn't. No, because do this. Okay, so type this in instead. 30 squared, in parentheses.
Squared. 900.
Okay, divided by, in parentheses, 3 times 10 to the 8th, that quantity squared.
Times 10 to the negative 14.
Okay, then 1 minus that, what you just got.
1
We could have just used this second answer, but that's okay.
1.
Okay, square root of 1, 1, times 1, 1. Yeah, at this speed, this is so low that your calculator, which was telling you things like times 10 to the negative 14th, right? So we know it'll go up to that far at least, is basically just spitting out 1. So how fast do we have to be going for this to actually make a difference? We usually think about it in terms of amount of the speed of light. So 0.5 c, 0.6 c, or whatever. And a nice thing about that is that we can just, since this already has c in it, if we're talking about 0.6 c, we just put 0.6 over 1 as this. Since they're both, we just put them both in terms of c, and they will reduce out. But that's about length. Now, we also have a similar one for momentum. And what's really cool about momentum in this way is that Newton, these are all maybe not direct refutations of Newton's laws, but they're truer than Newton's laws. Why? Well, Newton's laws break down at these speeds. the length of this, Newton's law is not really his specific laws, but Newton would have understood 1 meter to always be 1 meter, an immutable quantity in the universe, right? 1 meter is 1 meter. But the faster it goes in reality, the shorter it seems to get to outside observers, something Newton didn't account for. Okay, so a truer way to think about length is what was just said. So your height, in actuality, your height is not 1.8 meters, approximately, Justice. It's actually 1.8 meters times whatever speed you're going in that formula we just had, right? And for normal day-to-day basis, that doesn't change very much. But it's not technically right to say your height is exactly what you measure your height to be. And in the same way, Newton telling us, you remember the equation for momentum that Newton used to talk about force? P equals, no, P equals mv. This was Newton's equation for momentum. In fact, Newton, if you remember, talked about force as force equals momentum over time. So when Newton talks about force and his laws, in his Principia Mathematica, where he published the idea, his 3 laws, he actually talked about it in terms of momentum over time, which is neat because this has a relativity. Basically, this P, momentum, is a truer thing to talk about than force because the force can change depending on even the mass changes as velocity changes. So here's our new equation. Our relativistic equation for momentum is P equals mv over the quantity, the square root of 1 minus v squared divided by c squared. Hey, wait a minute. What's that look like? It's the same chunk. This is the same chunk of the, there's a word I think that your book uses for, that whole chunk there. I think it might just call it the relativistic factor. I can't find it at this moment in your book. But anyway, this chunk here is what we use to describe relativity mathematically. So at normal speeds, again, what is this whole thing reduced to at normal speeds? What we consider normal speeds, 1. And so this is true at our day-to-day speeds. P equals mv, that Newton said, is true at day-to-day speeds. But Newton would say, or he probably wouldn't say this, but according strictly to Newton's laws, if we keep a force on something, it will accelerate forever. But this tells us that that's not true. This tells us that the greater the velocity, the closer and closer this gets to what? Well, what would we have? What would we have if this velocity were c? Let's check that out. So we have c squared divided by c squared would be what? No, c squared divided by c squared would be 1. What would be 1 minus 1? 0. What's the square root of 0? 0. But now we have 0 on the bottom. Look, 0 on the bottom. If c is reached, 0 is in the denominator. And you thought Mr. Snitley was just pulling your leg about zeros on the bottom of equations breaking the universe. But basically that's what happens. If something that has mass approaches the speed of light, the universe spits out a divide by 0 error, and we cannot there's not enough momentum, there's not enough energy in the universe to make something accelerate to the speed of light. It cannot happen. If it has mass, the velocity can never, ever, ever get to the speed of light because of this equation. It doesn't happen. That's it. It does not happen. So what's the one thing in the universe that does go the speed of light? Light. And that means the converse of that, the corollary of that, is that light cannot have mass. Exactly. There cannot be mass because here's the next big thing. E equals mc squared. Basically, your book says, I love this phrase, the equation E equals mc squared is more than a formula for the conversion of mass into other kinds of energy. It states that energy and mass are the same thing. Energy and mass are the same thing. Your book describes the next sentence I love. Same thing. I'm going to write it on the board. Mass, your book says, is congealed energy. Mass is congealed energy. You have a mass, and that mass gives you energy. What kind of energy does your mass give you? Well, if you're not moving, but you're perched on top of the buttes, what kind of energy do you have? Potential. If you are moving, you have kinetic energy because of your mass. There's a reason mass is part of both of our normal, the energy equations we have talked about earlier in the year. And relativistically, if we're going at relativistic speeds, E equals mc squared over, guess, this, the square root of 1 minus v squared over c squared, giving us another proof, a mathematical proof, that again, we can never reach c, because what would energy turn to? If we get 0 on the bottom here, what would energy have to be? Well, no. We can have 0 energy. If this is 0 on the bottom, this would have to be what?
Infinity.
Yeah. If 0 is on the bottom, that's the same thing as infinity on the top. It would basically, there isn't enough energy in the universe to make anything that has mass go at the speed of light. But that's a silly question because there can't be. This is a more fundamental law of the universe than anything we've talked about this entire year. So you know not to ask questions like, what if there was about F equals ma? But you don't know because this is not part of our daily experience. But I appreciate the question because you're saying hypothetically, you mean, instead of theoretically, what if we could hypothetically make it reach the speed of light? What would happen? It would have how much energy? Infinite energy. It would be at least a Kugelblitz, which is what we call a black hole made entirely of energy, because again, mass is congealed energy. And so not just a black hole, but the whole universe would collapse in the same way that a black hole collapses from a star. The correspondence principle tells us, this is called the correspondence principle, tells us that the things that we used to think are true about Newton's laws must still be true for the theory of relativity. So it's still true. Why is this, in what way is this still true? Why was I able to teach you this at the beginning of the year? But we don't have what? Or at least not usually. Or at least, yeah, we don't go at velocities high enough for this to matter. So this is still true for our daily usage. This is still true for our daily uses. Your book also gives ones for time and length. Oh, we did the length one. But your book also gives time. This is how time dilates. Write this one down. This will be the last thing. Time equals time sub naught over, guess what? Square root of negative 1 minus the quantity v squared over c squared. So the time that seems to pass for an observer is equal to the time that seems to pass for the participant divided by our relativity chunk. Let's do it. One more thing. What if this is C? What if this is C? What does this all down here become? If it's C, 0. So now our time that we would have perceived, maybe 10 minutes, divided by 0 is infinite time. Time means nothing to a photon. For a photon, the universe has no space and has no time because it goes at C. All lengths are contracted to 0. All time is contracted to 0. Have a great day. Bye.